thing I should mention, I should get the paper back. These magnetic separates that I talked about did, since there was a wide array of them, one person did do detailed chemistry of each of the magnetic component and the non-magnetic component. And they're not identical, as you would expect. One has a lot of the iron-rich particles in it. So the magnetic component is more iron-rich than the non-magnetic component. I think there's a few other small other elements that have small variations. So for when people look at that with the mid-IR, you might be able to see small compositional differences between the bright and the dark.
So the separates do have big visible albedo differences,
yes,
right? Yeah. So that's the main thing that we would see in the diviner data, and that's something that Dylan has worked on, and Catherine Shirley, when we go into that simulated lunar environment or asteroid environment, atmosphereless measurement, the visible albedo exerts a really strong control on the thermal gradient in the top few hundred microns of that sample. And so that's one thing that Dylan showed in his.
They were offset.
Yeah, you start to see, especially at longer wavelengths, you start to pull up the emissivity. So that provides a kind of a visual distinctiveness, but it also could potentially complicate the analysis too. What changes are due to the albedo, which ones are due to any mineralogical differences. So that'd be something that'd be very interesting to look at.
Can I ask another question about that, actually?
Why don't you come on up, Carla? You're supposed to be up here. Come on. You need to get your steps in.
Let me pace around.
How are you able to create consistent samples that you can perhaps constrain albedo and then have the magnetic feature vary, or the other way around, where you have albedo vary but consistent magnetic?
Well, I don't have any of the magnetic separates, but they should still exist at JSC because Adams has turned them back. So one of the things on my sort of to-do list is to request those samples and remeasure them with modern, just to validate, make sure there's no other things that we should look at. But the data we do have, which I mentioned very briefly, is we do have size separates for individual soils, for highlands and mare, and those have been very carefully prepared in the curatorial facilities, so that we can be sure that they are the components that make up the bulk soil. So we compare the less than 10 micron, the 10 to 20, and the 20 to 45 compared to the bulk. And those size variations don't mimic what we see at the swirls, but there are compositional variations in the size separates. The finer particles are always aluminum rich compared to the bulk, basically because plagioclase breaks down easily, and you have a lot of plagioclase fragments more in the finer particles than you do in the larger particles. So there's all these complications but again, the sequence, actually I should look up, what I haven't done is look up whether the compositional variations we see in the size fraction, whether those trends are comparable to the compositional variations seen between the magnetic and the non-magnetic components. I can do that. I have the data for that. And that's a good idea. I should do that.
Those also sound like excellent samples to run in the simulated lunar environment chamber. So
they will be tiny.
we're working on that.
So, excuse, I'm completely out of place, perhaps, but this is for Dr. Prem. I was wondering more about maybe pulling on your thread a little bit further. If the levitating dust could create a boundary layer, sort of like the dust of the smog in like Delhi or something, that creates a thermal gradient between the surface temperature of the airless bodies, and if that would be perhaps sort of catalyzed by space weather interaction. So it goes back to like Lee's talk earlier. I don't.
So just to make sure I got the question right, but so the question was whether levitating dust grains could cause a thermal gradient?
And I guess it goes back to like Mojave versus Black Rock. So the different areas of the lunar surface would have different compositions of the dust. So the levitation of the dust would create different thermal gradients in the different areas that you're looking at.
Due to the compositional differences. Yeah, no, I mean, that's, so for instance, Dylan talked about this a bit as well, but one of the things that Ben has done is constructing these Christiansen feature maps of the moon, which he uses to distinguish silicic or mafic regions of the moon. As an aerospace engineer, I never thought I'd be able to say silicic and mafic into a mic. But yeah, it's certainly true that those different materials would set up different types of thermal gradients as well. And I showed you plots for enstatite, but we are interested, especially in the lab, looking at other mineral phases and mixtures of minerals as well.
So just coming off a LiDAR conference, do you think a LiDAR like microwave sounder could actually provide you some better analysis of that?
So I know there are a lot of interesting things that you can do with microwave remote sensing, especially, and I see Dylan nodding, but I know there was a microwave sounder on one of the Chang'e missions, and I know Matt Siegler has done some interesting work looking at internal heat flow using the microwave data. So yeah, I think there are interesting things you can do with microwave remote sensing.
Perhaps with the levitation of the dust, you could extrapolate some.
Yep. Thanks.
That discussion just inspired me to ask another question. Speaking of the uppermost surface and levitating dust, et cetera, recently I've been in a discussion about the fairy castle structure, okay? And that wasn't in your model, which is more layered, okay?
Yeah.
But clearly, this kind of structure must affect the mid-infrared as well as what it does in the visible. And in the near-infrared, one of the papers we did with our colleagues in Japan was pointing out for both the Kagaya data and the M-cube data, when you compare the brightness of a lunar sample, a well-developed soil, with as much, no packing, just best lunar soil, for, I think, 4 different Apollo sites, compared to the brightness measured remotely, the samples are always brighter. And we first noticed this when Clementine data came out, and everyone who does photometry say, Clementine data is too bright. And we thought, well, it's the best we can do. And it turns out Clementine data were calibrated with Apollo 16 soil, because it didn't have any absolute calibration. So it again is consistent with what we see now with 2 independent instruments on 2 independent spacecraft, that the Apollo soils measured in the laboratory are brighter than well-developed soils measured remotely. And the hypothesis is that that's because remotely you've got the fairy castle structure, whereas we don't have that in the laboratory. All we can do is just have a very remote surface. Can you model that at all in the mid-IR? Because that must affect some of the gradients that you're talking about.
Yeah, I think that's a really interesting problem. And I think just that very uppermost layer of the lunar surface is so interesting. There's so much going on there. In terms of modeling the fairy castle structures, I'm sure we could come up with some interesting way to do that. So, for instance, I think Marco Delbo and Bernacchi, Marco Delbo had a talk at AGU in which he was talking about some work that they're doing in which they're modeling the surface, they're modeling individual grains in the lunar surface, so they can stack those in fairy castle-like ways and they're using essentially a finite difference approach to really compute conduction and radiation between grains. So I think there's a lot of really interesting work going on in radiative transfer, both when we're looking deeper at these data sets, in terms of modeling, in terms of all the lab work that the Stony Brook group has been doing. So yeah, I think modeling that would be really interesting. I don't think we have sort of an established way of doing that yet, but I know there are people exploring those things, and I'd be really interested to see what comes out of that.
Yeah, Carly and I mean, so the T matrix, the superposition T matrix model that Gen's been working on, and Chip Leggett, another grad student, what Parvati showed, a figure from Gen's paper, is just kind of a cluster of spheres, because that's really easy to do. But there's absolutely nothing stopping us from building up each of those little particles into a fairy castle structure, and running a plane parallel light wave through that and seeing what comes out the other end. And the interesting thing is that we're not limited to just doing that in the thermal IR. We can do that in the Wisniar IR too, assuming we have the appropriate optical constants.
Well, because we do have data that can at least pin it, what you should get in the visible near IR, and then sort of. And then,
and I could tell us if we could do it right at those wavelengths, that we could believe.
I mean, it's ballpark. We don't have it exact, but we know approximately how much brighter and darker. Yeah, absolutely. Yeah, that'd be good. And then we can get photometry people.
Carly, related to that is the drift in the, probably related to that, is the drift in the heat flow temperatures upward, where we have destroyed, in deploying the heat flow equipment, we destroyed the fairy castle structure, and really did change the thermal characteristics of the uppermost portion of the regolith around those probes.
I was going to add that the addition of the simulated lunar environment chamber and the new maps I'll have for the thermal emission for channel 6 and 7 on Diviner will also show that difference, because we have Earth gravity in the simulated lunar environment chamber and you lose the fairy castle structure, but you still have the rest of the vacuum and illumination conditions.
There was a paper published by a Chinese scientist, and he actually modeled these very fluffy particulate surfaces in a fairy castle structure. I think it was in a journal of quantitative spectroscopy and radiative transfer. And if you're interested, Parvati, I can give you the reference later.
Sure. So was he using T matrix?
No, Monte Carlo.
So this was large enough grains that you could do ray tracing around them?
Well, yeah.
Yeah.
And he was, interested in snow, so just change snow to whatever you're interested in.
Yeah, I think, with the Monte Carlo stuff, another important thing to keep in mind, so it's something that can be applied at all wavelengths, but you need to make sure you're thinking, or I need to make sure that I'm thinking carefully about the wavelength compared to the particle size. So we've been trying to do Monte Carlo radiative transfer for radar as well, and we did some tests at optical wavelengths. I don't really have anything very intelligent to say, but this issue of particle size versus wavelength is important. So, for instance, if you're looking at if you're doing ray tracing, that really only works for large grains. I think, again, but yeah.
Right. Yeah. Well, he kind of combined both. He investigated both ray tracing and smaller particles, with me.
Yeah, I mean, I think it would be interesting to construct an elementary snowflake using, MSTM or something, and get the scattering properties of that, and then maybe scale it up using Monte Carlo. But yeah, lots of interesting stuff out there.
And sort of add to that, I mean, the lunar surface is a lunar surface, okay? So whatever works for the mid-IR also has to be consistent with what the near-IR. So we can't, if we could understand the actual character of the lunar surface, it'll feed into both of these. So it's different pieces of data have to give us the same answer.
You know, one of the reasons we had one of the cameras, Apollo cameras, with the black and white film was to do photometric studies, and I'm not sure any of those studies have ever been done. But there are a lot of zero phase photographs in the Apollo photographic suite. I was looking at some just the other day over at Station 2 that really are quite remarkable. And I suspect that USGS Archives has all the information about the camera and the calibration of the film and things like that. So, well, you have it all. Yeah, you have within those pictures, you have those photographs, you have the full spectrum, particularly in the panoramas. You know, the panoramas were upwards of 20 different pictures in 360 degrees in black and white, and with a good, you know, with good photometric control. Now, where the calibration data is, I don't know, but hopefully we can find it if you need it. Some of those studies may have been done. I just don't remember ever seeing them done. That was the object, though. That Shoemaker and Batson and others, that's the reason we had the black and white film in the camera was photometric study.
The photometry has been studied in great detail, both from telescopes and even with, you know, with the various instruments, including LRO, where you get through the zero phase. So we've got analyses of that. What we don't have is an actual physical model for what the particles are doing. You know, how narrow are the little holes? You know,
well,
what
in spite of my debates with Tommy Gold, you know, we did fly that camera.
Yeah, 3
and
times.
we do have photographs, and I think they're pretty good photographs of an undisturbed surface.
Millimeter resolution. It's pretty. I mean, there's a Helfenstein paper from last century, but yeah, I think there's a rich data set in the ALSCC, Apollo Lunar Stereo Close-Up Camera. That might be very relevant to this. They took it at 11, 12, and 14 in a variety of different environments, including actually on boot prints, so you have a little bit of control of what disturbed regolith looks like versus the. Oh, she's right.
And maybe you remember this. They did this, what they call the fly pisser, soil, and just get undisturbed soil for fly paper.
Yeah, they used velvet and beta cloth or something like that on 16.
Sarah was very interested in this, but when she actually looked at the product, it was not possible to reconstruct what the actual. It was a good experiment, good try, but it didn't capture what she was hoping for. You need to go back to the moon and get another experiment.
I would suggest.
Somebody has to define what that experiment should be.
I would suggest going back and looking at those ALSCC images, and because you can get them in stereo and construct a 3D model even. And I know that they've been re-scanned and digitized as part of the ASU effort to archive all of the original Apollo scans. And there was this one Helfenstein paper from late last century talking about the photometric properties based on what we see on those stereo camera images.
Yeah, sounds interesting.
Yeah, someone should do that.
Yeah. And just, I guess one last comment before we clear up. But you know, another something else to look forward to is the Korean Pathfinder lunar orbiter is going to have a polarization camera, and I don't think anyone's ever looked at the lunar surface in that way, from telescopically, but not from orbit. And Linja, I forget Linja's last name, but she and Paul Lucy have an interesting poster on some lab work they've been doing on measuring polarization properties of lunar soils.
Poster number 11.
Yep. Yeah. I think that's it. But I guess that's it, folks. So thanks to all the speakers and to everyone for a really great session. I was worried I'd have to ask questions about magnetism, but all I had to do was like try and nod and look intelligent. So thank you. And we do have the focus group sessions starting soon. So in this room, we'll have volatiles, and also in this room, we'll have Addie and the dust and plasma gang. So I guess we're having a joint dust, regolith, atmospheres, plasmas, volatiles focus group. But after that, we will reconvene for the next plenary session at 1:45.
Thank you.
That was a good session.